Assalamu alaikum wa rahmatullahi wa barakatuh. This is Reem Naguib, lecturer and preceptor of clinical pharmacy at King Khalid University. I'm going to be discussing today a very interesting topic, that is arrhythmias. So before we start, let's take a quick look at the term arrhythmia. Okay, you see, A means abnormal, rhythmia means cardiac electrical conduction. So the spectrum of diseases that we are discussing today is the disturbance in the electrical conduction inside the heart. Okay, so before we get into the details of this disturbance and the normal even electrical conduction, we need to understand that there are two basic properties, two essential properties of the heart. These are the electrical activity and the mechanical activity. Electrical activity, that means the movement of electrical charge inside the cardiac cells and muscles, which is then translated into contraction and relaxation. That is the mechanical activity. So there is a synchronous interaction between these two properties. They have to be coordinated, and any loss of coordination between these two properties will lead to many problems. Okay? So what is the normal electrical conduction inside the heart? As you can see from this figure, okay, the electrical conduction is initiated at a very specialized bundle of cells called the SA node, the sinoatrial node. These are specialized cardiac cells that can initiate cardiac activity or electrical activity. Then the electrical activity moves through the atria of the heart and then collected at the AV node, which is the atrioventricular node, and then the electrical conduction is conducted to the both ventricles through the bundle of His, okay, and then the right bundle branch and the left bundle branch until it reaches the lateral walls of the heart through the His-Purkinje conduction system. So this is the normal flow of electricity inside the heart. Remember when we talked about the electrical mechanical synchronization? That means each step of this pathway is translated into mechanical activity. Okay, so when there is a firing by the SA node, when there is an electrical discharge by the SA node, it will be translated into atrial contraction. Atria are the upper chambers of the heart, okay? And then the AV node and the conduction in the lower part of the conduction system, excitation will develop ventricular contraction. Okay? And of course, as you know, each contraction should be followed by relaxation. No cardiac chamber can be in the contracted state all time or in the relaxed state all time. There should be a contraction followed by relaxation. Okay? This is what the ECG shows us. ECG means electrocardiogram, so it's a representation of the electrical activity inside the body. And each of these steps is translated into a certain wave on the ECG. So the first step here is the electrical firing of the SA node, okay, and which is translated into atrial contraction. This is visualized on the ECG as what is called the P wave. So the P wave represents the atrial contraction, okay. Then the electrical conduction reaches the ventricle through the AV node and the His-Purkinje system, okay, and the ventricles contract. This is then presented on the ECG by the QRS complex. So the QRS complex is the ventricular contraction or ventricular depolarization. Depolarization electrically okay, is translated into contraction mechanically. So each depolarization is contraction, and each repolarization or hyperpolarization is relaxation, the opposite, okay? And as we said before, that each contraction should be followed by relaxation. So this is the ventricular contraction, and the next wave is actually a measurement of ventricular relaxation or repolarization. So you have P wave for atrial contraction, and then QRS for ventricular contraction, and then the T wave for ventricular relaxation. So where is the atrial relaxation? Actually, atrial relaxation is right here. So you see that atrial relaxation occurs at the same time of, more or less the same time, ventricular depolarization or contraction occurs. So the atrial relaxation is actually masked by the QRS complex. It's behind the QRS complex so that we cannot see it, okay? So this is a summary of the action potential and the subsequent mechanical activity. So we have atrial depolarization, meaning atrial contraction and release of blood into the ventricles, as you can see. Then the ventricular depolarization and contraction, so it releases blood into the major blood vessels, either pulmonary artery or the aorta, okay? And then ventricular repolarization, which is ventricular relaxation and filling of blood. So what these two complex figures represent is the action potential, that is the electrical conduction, but at the cellular level. So imagine that we took some cells of the sinoatrial node. Sinoatrial node is the pacemaker, as we mentioned before, this one, okay, this is the sinoatrial node, and some cells from other cells in the myocardium that conduct electrical activity. So this is what this figure represents: the action potential in the pacemaker cells, that is the sinoatrial node and similar cells, and this is the action potential in other cardiac cells that only conduct and not produce electrical activity, okay? What I want you to notice in both these figures, we will not enter into the details of these figures. I just want you to notice that the action potential or the electrical activity at the cellular level is nothing but movement of ions, specifically movement of cations that are sodium, potassium, and calcium throughout the cell membrane. So depolarization and repolarization is just a different concentration of ions, giving a total of positive currents or negative currents across the cell membrane, which generates action potential and electrical conduction. You will find this here, the sodium, the calcium, and the potassium, and also here the sodium, the potassium, and the calcium. Okay, remember these three ions.